A red ball begins moving from A, and simultaneously a blue ball begins moving from B. A travels with a uniform velocity of 50 meters per second to the right, and B travels with a uniform velocity of 25 meters per second to the right. Let's watch it again. And they happen to meet at some point C. The initial distance between A and B is 200 meters. How long would it take for the red and blue ball to meet at point C? Let's first solve this the traditional way, that is, using the equations of motion, and then let's solve it again, but using the concept of relative displacements and velocities. We'll focus first on only the red ball A. It travels from A to C with a uniform velocity of 50 meters per second, and we will use the second equation of motion but without any acceleration as the ball A travels with a uniform velocity. And we fix the origin at point A. The initial displacement at A is 0 as the ball begins there, and the final displacement is the distance between A and C, xac, which is unknown. The initial velocity is 50 meters per second, and that is the velocity right through. Using this, we obtain our first equation, that is equation 1. Now let's do exactly the same steps for the blue ball. Now we focus on the blue ball or ball B, and it travels from B to C with a uniform velocity of 25 meters per second. Again we use the second equation of motion without the acceleration component, as this ball also moves with a uniform velocity. Our origin is at A, so the initial displacement is xab in this case, which is given to us as 200 meters, as the ball B begins from this point. The final displacement is the distance between A and C, which is xac. And the initial velocity is 25 meters per second, which is the velocity right through from A to C. Using this, we obtain our second equation, which is equation 2. If we subtract the second equation from the first, we find that the displacement term xac cancels out, and we get the time as 8 seconds. Now let's look at an alternative way to solve the same problem, but this time we will use the concept of relative velocity. When we solve a problem using the relative velocity, the first step is to attach the frame of reference to one of the objects and then set up the equation viewing every other object through this frame of reference. So we will attach the frame of reference to A. Now A moves from the ground frame of reference at 50 meters per second, but not from A's own frame of reference, since ball A would be considered to be at rest from its own frame of reference. So we will have to view B's velocity with respect to A and also B's displacement with respect to A. And the good news is that we can apply Newton's laws of motion in any frame of reference as long as the displacements, velocities and accelerations are defined with respect to that frame of reference. Here the velocity of B with respect to A will be Vb minus Va, which is minus 25 meters per second. So A will really be seeing B approaching it along the negative direction of the x-axis. This is the animation as seen by an observer in the ground frame of reference. So now let's step into the shoes of A and check out how A would see this very same situation. Now this is the scenario from A's frame of reference and not from the ground's frame of reference. This is how A would observe the situation. The initial displacement of B would be B with respect to A, which is given as 200 meters, as the origin of the frame of reference is at A. And the final displacement would be 0, as B will meet A here with A being at rest. And B is approaching A with the velocity of B with respect to A, which we had computed as minus 25 meters per second to the left. Now let's plug this into Newton's second equation and check out how A is seeing B. So we get the final displacement minus the initial displacement equals the initial velocity times the time, and all this in A's frame of reference. And the accelerations of both A and B are in any case 0, so there is no relative acceleration. So substituting the values, we obtain 0 minus 200 as minus 25 t. Solving, we get the time t as 8 seconds. So you can see that by using the relative displacements and velocities, we obtain the same answer but with fewer calculations. Rather, we could do the same just using a single equation without solving simultaneous equations. The method is to obtain all displacements and velocities in terms of the observer's frame of reference, and then to fix the observer as stationary and compute the displacements, velocities and accelerations with respect to the observer, and finally plug all this into the equations of motion to obtain the unknown quantity. And we could have very well made B the observer too, and in that case all the displacements and velocities would have been obtained with respect to B. It takes a little bit of time to get adjusted to this method, but as we move on further into the course, you will grow more accustomed to it and also be able to solve problems faster. In problems where there is, say, a collision between two bodies moving in a single dimension, one way to obtain the solution is to apply the equations of motion to both bodies and then solve for the unknown using simultaneous equations. The alternative method is to fix one of the bodies and to obtain the displacement, velocity and acceleration of the other body with respect to this fixed body, who is also the observer. Then we apply the equations of relative motion to just the moving body.